Everyone, welcome back. So the first part of this class is about the basics of power systems, and I make the book in just 228 slides. So let's go one by one. I want to go slowly from the beginning because some of you are not familiar with electric circuit and power systems. So let me start with the power system fundamentals first. And so we start with the definition of phasors. Okay, so you remember the electric circuit, which has the voltage source, and we have voltage and current and resistance, capacitor or coil. So, but power system is an alternating current system, AC system. And we assume that the power system, in a normal condition, it is a stationary system. That means the frequency is constant all the time. And the frequency is 60 hertz, as you know. So the voltage is expressed as a sinusoidal, like that. So Vmax is the amplitude of the instantaneous voltage, and omega is the angular frequency. So omega equals 2 times pi times f, so 120 pi. So cosine omega t plus zeta v. Zeta v is a phase angle of voltage. So voltage fluctuates over time, okay? And because this is a stationary system, the frequency is just constant. Actually, in reality, frequency can change slightly, like plus minus 0.1 hertz. Or 0.2 hertz. After that, the power system may break down. So the role of power system engineer is to keep the power system stable. Okay, but this is just for easy analysis, and we assume that the frequency is constant. Okay, so that omega is 2 pi times 60. Similarly, because the voltage source, the voltage is fluctuating over time, the current also fluctuates over time. Okay, so that's why we have the kind of another sinusoidal form, I max times cosine omega t plus zeta I. So here we see two different angles, zeta v and zeta I. That means because this is an AC system, the phase of voltage and the phase of current can be different. Sometimes they can be same, especially for the resistance component. The phase of current and phase of voltage can be the same, but for the reactance component like coil or capacitor, the angle zeta v and zeta I are different. Okay, so yeah, we have this alternating current system. And then, yeah, you may heard of this terminology, root mean square, RMS voltage of the sinusoidal voltage. Because it oscillates over time, we want to quantify a number that specify the magnitude of this sinusoidal waveform. And the definition of root mean square is actually the average. But this average is taken over the squared voltage, and the average of that and the square root of that. Okay, so integration over one period. This one period is 1 over 60 second, because the hertz is 60 hertz. One period is 1 over 60 second. So integrate the square of the voltage over one period of time and take the average and take the square root of that, gives us the magnitude of the voltage. And so this is our symbol. So if you do simple math, just plug in the instantaneous voltage here, and you can get this formula. So I think you are familiar with that. That means the magnitude of the AC voltage is the amplitude of the instantaneous voltage, Vmax, over square root of 2. Okay, so Vmax is square root 2 times magnitude of voltage. So then we have a phasor representation. To introduce phasor, we need to use Euler formula. Euler formula is that, so e to the j theta equals cosine theta plus j sine theta. And using this phasor notation, let's see. Phasor notation is developed by rewriting the Euler, using Euler's identity. Okay, so this is what we have before. Instead of Vmax, this is replaced by square root 2 of absolute value of V. And so this can be expressed as like that, using this Euler formula. This is complex number, and take the real part of that. RE means the real. Gives you that one. So here we see a complex number here. Okay, and anyway, still, we have omega t. So this is a complex value, but it oscillates over time, and we take the real part of that gives us the instantaneous voltage. So then why do we need to use phasor notation or complex phasor? The heart of a phasor is that because assuming that our AC system is stationary, again, stationary means the frequency is constant, just 60 hertz. So as long as the power system is stationary, to describe this AC voltage or AC current, we only need to specify the magnitude and the angle. Okay? These are two variables. We don't need to care about the frequency itself, because the frequency is just 60 hertz all the time. So, given complex phasor, we can determine sinusoidal waveform as long as we know the magnitude and the phase angle, and vice versa. Okay, so yeah, now this is a phasor notation. In phasor notation, by the way, here we have this complex number, and still we have omega t. This is not a phasor. This is just a representation of continuous sinusoidal voltage using complex number, and just take the real part of that. But phasor removes this part because the frequency is all the time 60 hertz. So we don't need to write that. We don't need to keep it. Okay, to make it simple, in phasor notation, we do not have omega t term. Okay, we only have the magnitude term, this absolute value of V, and the theta V, the angle. Yeah, so the phasor notation of the voltage is the magnitude of the voltage, absolute value of V, and that the notation absolute value of V is the root mean square of the instantaneous sinusoidal voltage, and the phase voltage angle, theta V. Okay, so either two expressions are okay. The kind of Euler formula, or just the magnitude and the phase angle. Okay? They are used interchangeably. And that implies, so even though we are using phasor and we focus on the stationary behavior, we can always go to the instantaneous voltage that fluctuates over time like this. Okay, so the instantaneous voltage is again the real part of that, and that means the amplitude versus magnitude. I want to use these two terminology differently. Okay, amplitude is the amplitude of the sinusoidal wave, and the magnitude is for this phasor. Okay, so this is V max. This is amplitude, because we say amplitude of a sinusoidal wave. That's the definition of amplitude. By the way, this is the magnitude. In power system engineering, that absolute value of V means this one, but some other electric circuit theory, it may refer to that one. So please don't be confused. Okay, so here we are using this relationship. So this is the root mean square of the instantaneous voltage. Anyway, so yeah, this is the instantaneous voltage, and take the real part. That's the, yeah, this is a complex instantaneous voltage, and take the real part, and that is the instantaneous voltage. Or no, that V phasor. I need to use the, anyway. So no, that is the complex number. So we have a real part and imaginary part, obviously. And similarly, the current can be defined using the phasor, using the magnitude of the current and the angle of the current, like that. Okay. In this textbook, we do not use voltphase or var notation. So some textbook use this kind of volt notation or this kind of bar notation to denote complex number, but this slide does not use this kind of notation. So please don't be confused. Okay. And also note that the convention in power engineering, yeah, I told you, is that the magnitude of the phasor is the root mean square voltage of the waveform. Okay. Contrast with circuit analysis. Okay, so why are we using phasor? So the reason is because otherwise, when we analyze this circuit, a huge circuit, actually, the voltage changes over time, current changes over time, and then to analyze the circuit, you need to solve what? Differential equations. Right? You need to solve differential equation, and in the circuit, when you have, okay, we have a voltage source, we have a resistance, we have a coil, we have a capacitance. This is the most basic AC circuit. We have R, L, C, and to determine the instantaneous voltage and instantaneous current at any given time, you need to solve second order differential equation. Okay, and of course, there is a for ordinary differential equation. You need to solve this ordinary differential equation, and you learn this in engineering mathematics chapter 2, right? And at the time, all kinds of ordinary differential equations need to have the initial condition. At time 0, what was the charge? What was the initial amount of charge in this capacitor, or the initial current at this coil, etc. But as time goes on, we quickly go through this transient phase, transient period, and go to a stationary region. Okay, and after that, we can apply phasor, right? So then if you only focus on the stationary behavior, you don't need to solve this ordinary differential equation. Just focus on phasor only. And then everything about analyzing this AC circuit is very similar to analyzing DC circuit in this phasor domain, right? So for example, V times IR, Ohm's law. Similarly, you can apply V times IZ. This is impedance, something like that. So here, we have a time analysis. This is applicable at any time, but it requires solving ODE. Okay? Anyway, but if the system is stationary, then we can apply phasor, right? So anyway, we have three components: resistor, inductor, and capacitor. So V times IR, that is same for instantaneous voltage and current. So V of t equals R times I of t. In phasor domain, that is a V times Ri. Here, that capital V and capital I are phasor, complex number. Okay? And about the inductor part, this relationship. I think you'll learn that in high school. Maybe not. Or, yeah, but the voltage drop around this coil is like that. So when current changes, so because this is coil, it impedes the current, and the relationship between the voltage drop over this coil is proportional to the change of current. Okay, and the proportional component, the coefficient is L, right? So L here. Similarly, if you take the integration of current over time, you can compute the total amount of charge in this capacitor, like that, from 0 to t. And so the voltage at time t of the capacitor is this plus the initial voltage. Okay? So, but if the system is stationary again, okay, so I need to go back to that point. So from here, using the phasor notation, you can go there. Okay, so yeah, R, L, C, and the impedance, so resistance. But in a complex domain, we use the terminology impedance, and the notation is Z. Okay. And for this resistance, still this is same R, but for this reactance component, this component is J omega L. And this part is 1 over J omega C. Here omega, again, omega is 2 pi F. Okay, actually you can derive from here to there, just applying the definition of the phasor. Okay? Do it yourself if you are not sure what that means. You can do that. Also here, yeah, Z is the impedance, and impedance is R plus JX. So here, X can be either this one. So sometimes we use this is XL and this is XC. Okay, so R plus JX is the impedance, and we have the impedance magnitude and impedance angle. But please don't be confused that this impedance is not a phasor, because phasor needs to include oscillating component, the 2 pi F component. This is just a complex number, not a phasor. Okay, and so when we have impedance, R plus JX, the magnitude of that is obviously, using Pythagoras law, square root of R squared plus X squared. And the angle is arctangent X over R. Any questions so far? Easy. Obviously. Yeah. Let's look at one simple example here. We have one voltage source and resistance and coil, 4 ohm, 7.96 millihenry. And this voltage is 100 volt, because this book is written by American, so they use 100 voltage. We are using 220 voltage, right? And this is instantaneous, the V max, so square root 2 times 100. If you want to feel the voltage, you can just plug into into the outlet like that. Okay. This is kind of safe, because the current does not go through your heart. So it's just okay, but don't try to do that. But yeah. But this can be harm your heart, okay? Because the current go through your heart. So anyway, yeah, just joking. Don't try to do that. Any of this. Anyway, so this instantaneous voltage is like that. This is the amplitude and omega, and the voltage angle is 30 degree. Frequency, yeah, 60 hertz. Japan, Europe, 50 hertz. Right? So it depends on the continents. Actually, in terms of standard, power systems or communications, the standard of North America and Europe are typically different. The reason is because to protect their market. Okay. Anyway, so R, the resistance is 4 ohm, and X omega L is that one, 3 ohm. Oh, so that 7.96 millihenry was chosen carefully to make this X as 3 ohm. Okay. Then the impedance magnitude of that is 5, and this angle is 36.9 degree. Yeah, then you can compute the current using phasor notation. Complex current I is V over Z. So like Ohm's law, we have this very fundamental, simple but fundamental relationship. Complex voltage, complex current using phasor notation and impedance, we have this relationship. So I is V over Z, here V using the phasor notation, magnitude 100, angle 30 degree. Impedance Z is what? This one. Magnitude is 5, angle is 36.9 degree, like that. So amplitude is divided by 100 over 100 by 5, so that gives us 20. And the angle is, how can you compute this angle? Just this minus that, right? That gives you minus 6.9 degree. And this is the current, so ampere. Then, this is a phasor notation. And from this phasor notation, you can recover the instantaneous current like that. Magnitude, and this is amplitude, square root by 2. And same frequency, omega t, and the angle is minus 6.9 degree. Okay, so this is instantaneous current. Okay, 강의영상, are you okay? Not much. Not maybe. If you are not okay, that is because I jumped from here to here. But if you know Laplace transform, you can directly go from here to there. Okay, take the Laplace transform of this, then you can get this one. Okay, and after applying Laplace transform for AC instantaneous current voltage, you can get stationary phasor system that is very similar to the DC circuit. Okay. Okay, so we talked about complex voltage and complex current and the phasor notation of these two, and now it's time to define complex power. Okay, before we define complex power, let's talk about the instantaneous power first, because this is the physical quantity. What I mean by physical quantity, that means complex power is not a physical quantity. That's a mathematical notion, just for convenience. Okay, please don't be confused. Complex power is not physical concept. It's just a mathematical modeling concept. But no, we can define power physically. That is instantaneous power. So when we have voltage and current, and they change it over time. And actually here we assume sinusoidal stationary system, but the definition of instantaneous power can be applied to any voltage and any current, even if it is not stationary. Okay? So the instantaneous power is simply voltage times current at any instance. Okay? That definition can be used whenever you want to apply. So instantaneous power is simply voltage times current, and here, in this case, our voltage and currents are sinusoidal wave. Okay? So we have that, and just plug in. And using this formula, 코프코는 두 코코, right? So you know that, 코프코는 두 코코. So the multiplication of two cosine terms gives you that formula. Okay. So just plug in and you get 1/2 1 over 2. So multiply these two, gives you 1 over 2 V max I max. And the difference term of these two, this omega t and omega t canceled out. So we have zeta V minus zeta I. And because of this term, we have 2 times omega t plus zeta V plus zeta I. This one. So this is interesting in the sense that our instantaneous power oscillates over time, but the frequency is twice as before. But also we have a constant component, this one. Okay. Then when you look at this, can you think something else? Instantaneous power changes over time. What happens if you take the integration that over one period? What happens? Take the integration. This instantaneous power is a sinusoidal waveform plus some offset, some constant term. So if you take the integration of that instantaneous power over one period, then you only have this term. No, sinusoidal wave and the integration over that over one period is 0, right? Obviously. This obvious. So what I told you is just this one. Now, I want to take the average power, not instantaneous power. So take the integration and take the average. Then you only have this term, right? And this part is the multiplication of absolute value of V and absolute value of I, or the magnitude of the voltage and magnitude of the current. And this cosine term. By the way, here we have zeta V minus zeta I, this term. And okay, let's see what happens if zeta V and zeta I are same. What happens? That means the phase of voltage and phase of current are same. What happens? Yeah, this is 0. Cosine 0 is 1. So this average power is maximized. And that happens here. For the pure resistors, the voltage and current have the same angle, right? What happens when they differ by pi over 2 or 90 degrees? When the angle of voltage and current differ by 90 degrees, cosine 90 is 0. So average power is 0. That happens here or here. So for the ideal coil or capacitor, the ideal coil or capacitor means that they do not have resistance component. And then they consume 0 power. Okay. So in the difference between voltage and current, this is an important one, and that is called power factor angle. Okay, and this term, cosine power factor angle, is called power factor. Okay, so power factor, usually denoted by PF, it stands for power factor, not proof. This power factor is one of the key components of AC power systems. Okay? And sometimes this angle is very close to 0. That's a good sign. But sometimes this angle increases somehow, usually when we add inductance load, or inductance load. When we add inductance load. So, okay, shortly I will talk about how can we make this angle as close to as 0. Okay, that is called power factor correction. So we want to maintain this power factor as close to as 1. Okay? Otherwise, it is not easy to deliver a real power. Any questions so far?
90도가 넘어갈 수도 있나요? 차이?
Yeah, why not?
파워가 음수가 되는데.
Oh, good point. Let's see. I never thought about that before, and practically that does not happen. Oh, interesting question. What is the meaning of negative power? Negative real power? Yeah, why not? Yeah, why not? Yeah, it can happen. Okay, so I will talk about that later. So we talked about the power factor, and that comes from here, that comes from this instantaneous power, and take the average of that. But let's focus on this one more time. We have a constant term plus sinusoidal term. And the second part, this one, we want to break it down into two parts. So this term is same as before, like this one. But no, this term can be break down into two parts using this formula. Is what? Kokosasa. No, Koko. Is it correct? Yeah, using this formula, we can break down the second term like that. So, okay, this term is same to that one, right? And then this plus that, so cosine, minus, so plus sine. You see that? And why do we want to do this? The reason is because this part is the instantaneous power into resistive components, and this part is the instantaneous power into a reactance component over here, electric and magnetic field component. No, this part. So why am I talking about this? So when you only focus on here and you focus on the instantaneous power in this AC system, anyway the instantaneous power, the P of t, that changes over time as a sinusoidal waveform, and the frequency is two times of f. Yeah, so what I want to tell you is, the instantaneous power here changes over time like this, and it has average of that, and this is t, and this part is this much, right? That's the constant term. And this sinusoidal part, okay, here, this sinusoidal part term has this times that, and also this term. So the amplitude of this sinusoidal term, this one, is determined by 1/2 V max times I max times cosine, the power factor. Okay. So, actually, but when the power factor changes, actually, it also changes the bias term, this term also changes. Okay. And by contrast, this L and C, it consumes instantaneous power, and the frequency is 2 times f, and the amplitude is this much. Okay? So the amplitude is sine the power factor angle. So when the power factor angle is 0, actually we do not have this term at all. So that is here sine, cosine, so they need to be different by 19 degree, plus or minus, but anyway, so we have, yeah, okay, and I draw this, yeah, something like that. Okay. So this amplitude is determined from here. So what I want to tell you is the power factor angle, theta v minus theta I, and the cosine of that, and this is power factor, and depending on the power factor, this amplitude and that amplitude changes, and also this bias term changes. Okay. So, okay, we talked about instantaneous power only so far. This is a physical quantity again. Now we define complex power. No, complex power is just a mathematical notion. And the definition is, okay, the symbol is S equals V times I conjugate. Just memorize it, okay? And using this definition of complex power, so if we use this definition of complex power, then it becomes easier to describe AC power systems. Okay, and then maybe you are curious, hey, why do we want to put conjugate there? I know the phasor of voltage, I know the phasor of current, then why not V times I? Because in the case of instantaneous power, just the instantaneous power is V times I. But in complex power, we need to put conjugate sign there. The reason is because when we derive the formula before, we see that average power is described by cosine, that cosine, theta V minus theta I. The angle of voltage and the angle of current. And to extract this kind of term from phasor notation, the angle of this is theta V. The angle of this is theta I. Then we need to put conjugate there so that the angle is now theta V minus theta I. Okay? So yeah, that's the definition. And yeah, that's the definition, and we have a real part, this one, and the imaginary part of that one. You see that? Just applying the definition only. So V so S equals V times I conjugate, and this is V theta V times I theta I, and then conjugate, so minus, so this is a V I, actually theta V minus theta I. Okay, so we have the real part of this and the imaginary part of that. So the real part is called active power. Imaginary part is called reactive power. Okay, yeah, here, real power is denoted by P. So this is real power components and the imaginary power component Q. Real power, this is the average power of instantaneous power. And the unit is watt, or kilowatt, or megawatt, or gigawatt, terawatt. What? Yeah, terawatt. Possible. No. Is it possible? Let's see. In Korea, one nuclear power plant generates typically 1 gigawatt. And the peak power of Korea is already over 100 gigawatt. And typically, the power consumption or generation of the United States is 10 times higher than that of Korea. And so is the GDP. Okay, so in the United States, the maximum power is 1,000 gigawatt, is 1 terawatt, right? And typically, US consumes, I guess, 20% of the total power in the world. So, the Earth consumes, I guess, how much? 5 terawatt maximum. Okay. Anyway, and then we have reactive power, and the unit of reactive power is, this is called VAR, 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 okay? Voltage, ampere, and reactive. This small r stands for reactive. Okay, so VAR or kilovar or megavar, etc. So that is the magnitude of power into electric and magnetic fields. And if you take the average of this reactive power, that is 0. So at any moment, we have instantaneous reactive power component, but when you take the average over time of reactive power, that becomes 0. Okay? And the unit of complex power is just voltage times current, so VA, or kilo VA, or mega VA. By the way, about the unit, this K is lowercase, and M or G is uppercase. But some people, some unknowledgeable people, are using like capital K, like this. But please don't do this. Small k, kilogram, same, kilometer. The unit of 1,000 is small k, not capital K. And the power factor is cosine pi, theta v minus theta I. And we say, I think you will be confused this, so please just focus on one part, this part. When the current lags voltage, then the power factor is called lagging. And that happens here. Lagging. So you know that V times Z omega Li at this coil. And using the phasor notation, you see that the angle of voltage is 90 degree ahead of current because of this J term, right? So here at the coil, the angle of current is lagged in reference to voltage. So that's the meaning of lagging. Or the current, am I saying correctly? Current lags, yeah, so that's why you are, I'm confused, you are confused. Yeah, just this is the naming, lagging. And why is it called lagging? Actually, yeah, so because this angle, this is theta v minus theta I, and it comes from the definition of complex power. The reference angle of pi is with respect to current, right? And in this case, so yeah, voltage, the angle of voltage is, how can I say, greater than the current. So it becomes positive. And anyway, this situation is called lagging. Okay? But you will be confused anyway later. So one way to remember this is to use some childish method to just memorize it. And my method is, coil is like that. Lagging, leggings, similar. Okay? And other part is leading. Okay, this will be helpful to you, hopefully. Yeah. So, and this is a power. This is triangle is called power triangle. We have real power and reactive power PQ, and the magnitude of that is the magnitude of complex power denoted by absolute value of S, and this theta is the power factor angle. Yeah. So for positive real power and positive reactive power, this pi is positive. Yes. So yeah, magnitude is like that. Pi, is it phi or pi? It is always confusing anyway. Yeah, phi, pi, etc. So arctangent of that. Okay. So the relationships between real, reactive, and complex power, again, P is absolute value of S times cosine pi. Q is absolute value S times sine pi. But please be patient to that. No, that can be either positive or negative. So that's why we put plus or minus sign there. Okay, and that is because, you know, no, the current can lead the voltage or voltage can lead the current. So depending on the situation, this part can be either positive or negative. Okay, so when it becomes positive for the case of this coil. It becomes negative for the case of capacitance. Okay, so example, a load draws 1 kilowatt with a leading power factor of 0.85. What are pi, the power factor angle, and Q and S, absolute value of S? Then, you know, the lagging is the plus, so the leading is minus. Okay, just memorize it. Don't try to, yeah, you can understand it, just memorize it. Okay, so lagging coil, this positive stuff. So arc cosine 0.85 and put minus sign here. So the angle is minus 31.8 degree. And when this is negative, it comes from capacitance. When this is positive, the reactive power is consumed by this coil. When this is negative, when the reactive power is negative, then the reactive power is generated from this capacitance. Okay, so the sign of reactive power is important. When this is positive, that is the consumed reactive power at this coil. But when it's negative, the reactive power is generated from the capacitance. It's slightly confusing concepts, still, but no. Just memorize it. Okay. And the magnitude of complex power is, you know, using the formula like that. So yeah, load draws 100 kilowatt. And we know the power factor, the leading power factor. And the magnitude of complex power is computed like this. So this is higher than 100, so 117.6 kilo VA. And the reactive power, you know, just using the definition, using this magnitude and sine phi or pi, and that gives you this number. This is negative. That means that component is capacitance, and it generates reactive power. Okay, so load consumes minus 62 kilobar, or load supplies 62 kilobar. Okay, and you know, you may think this is just mathematical stuff, but it's a real thing. This is important, especially in the sense that where we want to compensate the power factor, which means we want to make the power factor as close to as 1. Sometimes we need to put capacitance at the load side to inject reactive power. Okay? Why do we need to do that? Because at the load side, it consumes a lot of reactive power. When does that happen? That happens when this component is huge. When does that happen? When you use motor. The motor has a huge coil, so it has a huge inductance component. And then it changes the power factor. It changes the angle between voltage and current. So the power factor becomes small and small. And that's not good to deliver power from the source to the load side. Okay? So that's why we want to compensate the power factor at the load side. And one easy way to do that is just put capacitance component at the load side. Okay? Conservation of power. Okay, different topic. Any questions so far? Conservation of power means that at every node or bus, you know that node are same to bus. What it means, I didn't talk about the topology in this class yet, but in the spring semester we talked about power system economics, so many of you are familiar with that. So but I don't want to talk about that. But anyway, we have node, okay, or bus. Then, just the sum of real power into a node must be equal to 0, and the sum of reactive power into a node must be equal to 0. And this can be directly derived from Kirchhoff current law. Right? You are familiar with Kirchhoff voltage law and Kirchhoff current law. Kirchhoff is Russian. So in America, Kirchhoff is called Kirchhoff voltage law or Kirchhoff current law. So this is just a direct consequence of Kirchhoff current law. Because the reason is because what is the definition of complex power? There is V times I conjugate. You need to use this definition again and again and again. Later we will derive this kind of relationship. Again, here this Y is the admittance matrix of the power system. At the time, we still use this formula. I will talk about this later, okay? So you don't need to focus on this yet. Anyway, what am I talking about? Oh, so from here, anyways, from Kirchhoff current law, we have a node, we have many link, then the sum of the all incoming current becomes 0, right? Or all the sum of incoming current is equal to the sum of outgoing current, right? So the sum of that is 0. So when you put summation here, the summation can go there. So anyway, it becomes 0. Okay? So the sum of real power and the sum of reactive power at a node becomes 0. Right? They all share the same voltage, right? Okay. Let's look at an example. Here, power flow coming from source to load at bus. The source is 100 voltage AC. Voltage angle is 30 degree, and we do not have load. Actually, they are load, so 4 ohm plus 3 j ohm, the reactance component. And applying this definition of complex power S times V conjugate, so 100 and angle 30 degree. So we had that example here. Here, same thing. So we computed the current, this one. Yeah. Is it same? Yeah, same. So because I conjugate, so rather than minus 6.9 degree, this is 6.9 degree. So the complex power magnitude is multiplied and the angle is plus, so 36.9 degree. And the real part is the reactive power, imaginary part is that. So 1600 and 1200. Here, the power factor is the angle of that one, right? So cosine of that is 0.8. You see that? So 4, 3, 5, and this pi is 36.9 degree. This diagram comes again and again and again because 3, 4, 5 degrees 3, 6, 9, easy to remember. And yeah, the power factor is 0.8 lagging. This angle is positive, and this is about the coil, and then this is lagging. Okay. Yeah, and then the complex power at the resistance part, denoted by SR. So voltage there and the current. We have the same current for all components. So VR times I conjugate. VR is R times I conjugate. Ohm, 4 ohm times the current. Yeah, this one, and the current conjugate is that one. So when you compute this, it only has real part, no imaginary part. So it only has the active power, 1600 watt, and 0 reactive power. About the inductor coil, the complex power at the coil, VL times I conjugate, and this VL is the reactance component J omega L or JX times I. So this is the reactance, inductive reactance 3J times 20 blah blah blah, same thing. So when you compute this, this is purely imaginary, right? Because we have J term here. And the magnitude is 2400, so 1200 bar, and 0 active power component. Any questions? So you may be curious, hey, why are we care about this reactive power? I know that, at the load side, sometimes we have an inductance load like a motor, so that changes the angle. So yeah, we need to have a notion of reactive power anyway. But what is it? What is the reactive power anyway? Again, this is a mathematical concept, but it also has some physical concept, and that is like this one. It is about one of the important thing about reactive power is about the capacity of a transmission line. Okay, so when you drive through the highway, you can see the transmission line, huge transmission line, right? And then, the voltage is pretty high, like 765 kilovolt, or 345 kilovolt, or one more. The typical high voltage in Korea transmission line, 765 kilovolt, 345 kilovolt. What else? Yeah, 154 kilovolt. Anyway, so each transmission line, so we have a transmission tower. It is exactly like this, okay? Yeah, I put 3 arms there. So the number of transmission line is the the multiplication of 3. Okay, so that's why I put 6 arms here. And the reason is because maybe on Thursday, we'll talk about 3-phase system. Now we are only talking about a single-phase system. Actually, yeah, I didn't say anything about, but we are just talking about a single-phase system. But we will go to 3-phase system, okay? And because our current AC system is based on 3-phase, now we have either 3-line or 6-line or 9-line or 12-line, etc. So this is the multiplication of 3. And actually we have a tiny line here that is called neutral line. But anyway. Okay, what I want to tell you is, how can I draw this? We have this kind of transmission line. And the ideal transmission line need to have only the resistance component, but actually it has inductance component and also this capacitance component. The reason is because we have ground, and ground is 0 voltage. This is a very high voltage, like this one, or that one, or that one, okay? So even though the air is almost like an insulator, but because this voltage is very high, so when we have this ground and we have a high voltage line, we have a small capacitance component, okay? So anyway, this transmission line has the inductance component and the capacitance component. And also it has some very small resistance component. So from this resistor, the power is consumed and heat is generated. Okay, so I square R. This is the heat dissipated by this small resistance of the transmission line, and they just dissipate it into the air. Okay, this is the loss of the energy delivery. So we want to make this power loss as small as possible. So that's why power, instantaneous power P, so V times I. So for to deliver the same power, as long as this is same, we are delivering same power. But if we increase this voltage high, we can keep this current low, and this I square R can be small. Okay, so the reason why we are using this high voltage is to reduce the transmission loss. Okay, and what happens when this transmission loss happens? Okay, what happens? Yeah, what happens when this transmission loss occurs? Heat is generated here, right? And then the temperature of this line goes up, and then the line sags, okay, and then it can be further sagged, okay, and then maybe there are 3 here, and then this sagged line can touch this tree, and then this is very high voltage, this is 0 voltage, and this wood is kind of insulated, but if the voltage difference is so high, then current can go through from here to there, right? And then there is a short circuit and overcurrent flows, right? So that's why we want to limit the maximum current flows on this transmission line, and that defines the capacity of the transmission line. Okay. And then what's the role of reactive power there? Actually, not a role. What happens? So when we talk about the instantaneous power here, this is the power, this is the average power, or this is the active power that is delivered from the source to the load. But instantaneously, where I can see that instantaneously the current, anyway, the current goes up and down, up and down, up and down, and it's not easy to say, but anyway, this instantaneous power changes over time. And the important one is that if you take the average, you only have this component, but instantaneously we have a very high instantaneous power. And at the time, very high current, slightly higher current can flow. And that makes this kind of power loss. That means when we have more reactive power in the transmission line, when we have more reactive power in the transmission line, that means even though we are delivering the same amount of active power, but the instantaneous current can be higher. Okay? So that is why we need to keep the reactive power on the transmission line kept small. And so I say too much about this, but there is a very good analogy to understand reactive power. So we have a cup of beer, right? So you have active beer, you have reactive beer, and this is the capacity. Okay, so when there are too much reactive beer, you cannot deliver not so much of active beer. Okay, so the role of reactive power, the reactive power is required because this kind of load need to consume reactive power, but that needs not be provided from the source. That can be provided at the load side. Okay, why? Because we want to deliver as much as active beer. Okay. Yeah, so any questions? Power consumption in devices. So the resistor consumes I square R, so absolute value of I times R, and the inductor only consumes inductors only consume reactive power. So the inductor, the sign of reactive power is positive. Okay. Capacitors only generate reactive power, so this is negative. And the calculations are all same. You can use the definition of complex power. What I mean is when you have resistor or inductor or capacitor, always you can think of the voltage difference between these two or these two or that two. And you can think of the current go through here, there, right? And then just take the definition of the complex power as times VI conjugate. Okay? Using this, you can compute the consumed active power over reactive power. Another example. Yeah. And another example. We have 5 more minutes. Okay, why not? So 5 plus J 40 ohm, that's the impedance of the transmission line. And the load side we have 100 ohm. Wow, what kind of load is like that? Heater. Yeah, maybe. I don't know, maybe. So if you are curious, the typical type of load is a light bulb, right? Light bulb is the first invented electric device, right? So Edison invented light bulb, and so he wanted to sell the light bulb, so he constructed the transmission line with other guys, right? DC transmission line. And then Tesla disagree with that. Hey, DC, no. So we need to use AC. So that's why we are discussing AC now. Okay, anyway, so that load, 100 ohm, I think, so you know the light bulb, the 60 watt of light bulb, this is a very energy hungry component, right? It's like a energy hippo. Right? So if you use this kind of light bulb, that means you are very rich, or you are not quite caring about our environment. Anyway, what is the resistance of this light bulb, typical light bulb? How can you compute that? You can do that. How can you do that? Minjae, can you guess? Oh, the question was, what was the resistance of this light bulb? Purely resistive load. Yeah, the resistance of the filament. In ohm, how much is it? Hey, I gave you all the information. It consumes 60 watt. You know that we are using 220 volt. Then what? What? 60 watt. What is the resistance? How can you compute that? 경용? Yeah, so, yeah, so, here, this is 220 and 0 angle, and this current is Z over V. Here Z is just R. And this is actually conjugate, but no, this is real number. This is 60 watt, right? So if you compute that, the resistance is 80 ohm. Is that light bulb? I don't know, but anyway, so that has that kind of dimension. Let me stop here, and I will